Ever heard the rumor? There's an engine out there so small you could cradle it in your arms, yet it packs enough punch to do what only supercars dream of, generate 1,000 horsepower. Sounds like magic, right? Buckle up, because today we're going to break down why Formula One's 1.6-liter V6 engine isn't just a miracle of power, it's a wild, brain-twisting ballet of pure engineering genius. Imagine, for starters, your mom's everyday sedan. It probably has an engine bigger than this one, but compare the horsepower, and the F1 unit would leave her car and most others eating tire smoke in disbelief. At just 1.6 liters, smaller than the 4-cylinder in a grocery getter, this engine flexes harder than a Bugatti Veyron. So, how is this possible? Let's unlock the puzzle, piece by mind-blowing piece. Let's start with numbers that'll shock any car enthusiast. 15,000 revolutions per minute. That's where Formula One engines hit their stride. To put it into context, the red line for most road cars is 6,000 RPM, maybe 7,000 if you're driving something sporty. F1 engines spin at 2.5 times that, launching each piston up and down 250 times per second. That's right, each little metal cylinder in this engine is moving faster than most fighter jets, and the stresses involved could end careers for lesser machinery. Now, try to visualize this. At full speed, the connecting rods inside the engine endure forces exceeding 6 tons. Imagine suspending an elephant from each rod, and then lifting and dropping that weight 250 times every second. Oh, and the pistons themselves? They accelerate at over 8,000 times the force of gravity, enough to black out a fighter pilot 1,000 times over. This is a savage dance, and to keep it going, F1 engineers use super exotic metals. Pistons forged from aluminum beryllium alloys, valves crafted from titanium aluminide, materials that regular mortals rarely see, but they become the backbone of survival at these staggering RPMs. Each piston costs more than a whole engine in a regular car. Each valve rivals your monthly rent. But that's just the opening act. If you think turbos are old news, think again. The turbocharger on a Formula One engine spins at, wait for it, 125,000 RPM. That's tip speeds reaching Mach 2, twice the speed of sound. At these insane velocities, the tiniest imperfection could shatter the delicate balance. So every surface is polished to a mirror shine. If someone left a fingerprint, the whole unit would threaten to explode. But the real magic happens with the boost. F1 engines operate at 5 bar, about 73 psi. For context, your buddy's tuned Subaru pushing 500 horsepower might run at 20 psi, maybe 25 if he's feeling brave. But F1 power units triple that, cramming air into the engine till it's over 200 degrees Celsius. That's 400 degrees Fahrenheit. That means every bit of air is so hot you could bake cookies in the intake. So, what do the engineers do? They developed intercoolers on the bleeding edge of technology, microscopic passages crafted via computational fluid dynamics, more advanced than NASA's spacecraft. It chills that inferno down, prepping it for combustion. But here's a twist. The turbo isn't just a hot air pump, it's married to something NASA probably wishes they invented first, the MGU-H. This is a motor generator unit that sits right on the turbo's shaft. When the driver lifts off the throttle, instead of losing all that energy to heat and inertia, the MGU-H harvests it, stores it, and keeps the turbo spinning at optimal speed, ready for the next power burst. Goodbye turbo lag forever. Enter the hybrid side of things, where Formula One truly leaps into the future. The MGU-K, or motor generator unit, kinetic, is just as space age. Connected directly to the crankshaft, it can instantly throw an extra 160 horsepower into the mix. Every time the driver hits the brakes, the system switches into generator mode, grabbing kinetic energy and pumping it into the car's energy store. And speaking of the battery, it's compact, about 50 pounds, but it can store up to 4 megajoules of energy. Sure, that doesn't sound like much, but during those frantic laps, it's enough to power a normal house for an hour. And this little powerhouse is charging and discharging constantly, handling current flows that hit 1,000 amps. Engine management? You guessed it. On another planet entirely. Every millisecond, the computer brain makes micro adjustments to ignition timing, fuel injection, boost pressure, and energy deployment, all while 1,000 sensors paint a vivid picture of what's going on inside. There's more real-time analysis happening in a Formula One engine than in most scientific laboratories. But the internal combustion side, that's where the truly wild stuff happens. With compression ratios reaching 14:1, boosted by 5 bar of pressure, the cylinder pressure pressures hit 300 bar, that's more than 4,000 psi. Regular engines wilt under half that force. To contain such energy, F1 engine blocks are sculpted from solid billets of aluminum via 5-axis CNC machines. Cylinder head bolts are made of Inconel, ultrasonically tested for flaws that can't be seen by the human eye. Don't forget the fuel system. Direct injection here means firing petrol at pressures up to 500 bar, several times what a road car can handle. Each team has bespoke blends of fuel, carefully engineered for peak performance and reliability, and to keep things fair and challenging. The flow rate is fixed at 100 kilograms per hour, less than a third of what NASCAR engines guzzle. F1 engines produce twice the power with a third of the fuel. How? Lean burn combustion. The engines run with huge excess air, boosting efficiency but making combustion extremely unstable, as if you were trying to run a campfire with wet wood. Keeping the flame lit requires a monster ignition system. Think plasma ignitions and pre-chamber jets. Small chambers above the pistons produce a super rich mixture, lighting up the lean main mixture with jets of fire like controlled explosions inside explosions, and leading to faster, more complete burns. And just in case you're wondering how the valves survive all this, they don't rely on metal springs anymore. Pneumatic valve springs, powered by nitrogen at over 20 bar, keep everything moving safely at 15,000 RPM. A feat mechanical springs couldn't dream of achieving. Here's an odd detail. Despite their high-tech nature, F1 engines don't use variable valve timing, not allowed by regulation, so cam profiles are meticulously calculated, tuned for every possibility in the entire rev range, like expecting a marathon runner to sprint, leap, and jog perfectly without shifting gears. Let's talk about heat. These engines throw off more than a megawatt of waste heat, enough to heat 50 homes. Their radiators and coolant systems are marvels, designed with the kind of precision that would make aerospace engineers cry tears of envy. The coolant is a custom blend of glycol and special additives, preventing vapor bubbles that could destroy cylinder walls, and the oil system is equally wild. Dry sump lubrication with pressures over 10 bar, synthetic oil formulated to handle unimaginable loads and temperatures, and jets that cool the underside of the pistons at 100 miles per hour. And you know what's even crazier? The engines are designed to last about 5,000 kilometers, just 3,000 miles. But in those miles, the engine will spin more times than your road car engine will in its lifetime. Every single clearance and tolerance is so tight that the engine must be preheated before it turns over. If not, the parts wouldn't even fit together. Before any engine hits the track, it's put through merciless dyno testing, gear changes, cornering, straight bursts, simulated on dynamic test benches. Every gear shift, every throttle crack is measured, every ounce of power and torque logged to surgical precision. Delivering power at the flick of a pedal is crucial. Modern F1 engine mapping, and even artificial intelligence, predict what a driver wants before the command is sent. In some cases, the software is running millions of lines of code just to keep the orchestra perfectly tuned. But what about the sound? Older generations mourn the thunderous cry of naturally aspirated V10s and V12s, but today's 1.6-liter turbo hybrids are strangely quiet. Efficiency rules, and every decibel lost to the exhaust is wasted energy. Modern F1 turbos double as mufflers, and complex exhaust systems are optimized to channel every bit of exhaust to boost, not to sound. Some teams have tried adding speakers or redesigning the exhaust for more drama, but at the end of the day, speed trumps theater. So what's the math? Peak power hovers around 1,000 horsepower at 11,000 RPM, with a robust power band stretching from 9,000 to 15,000 RPM. Torque, 350 Newton meters from just 1.6 liters, a figure that would embarrass much larger engines. Specific output crosses 625 horsepower per liter. High-performance road cars tap out closer to 100 or maybe 130 by stretching. Brake mean effective pressure? Well over 50 bar compared to standard road cars at 10 bar and hot hatches at 20. Here's the kicker. Thermal efficiency is above 50%. Some engines touch 52% in testing. That's better than many ship engines that are stories tall. Molly-jet ignition, F1's secret sauce. Some of this magic flows from systems like Molly-jet ignition. Instead of a single flame front moving through the cylinder, there are multiple jets shooting fire from pre-chambers for quicker, more thorough burning. The exhaust gases reach a toasty 900 degrees Celsius, enough to melt most metals. The exhaust manifold glows cherry red during a race, and it's built from Inconel or similar exotic metals just to survive. You might be amazed to learn just how disposable these masterpieces are. F1 engines are only expected to last a handful of races. Manufacturing tolerances are so tight, and the stress is so immense, that even a microscopic particle out of place can spell disaster. Every engine is tracked, monitored, and rebuilt frequently, disassembled between races, inspected under electron microscopes, and analyzed for the slightest hint of fatigue or cracks. They're forensic engineering's finest hour. There's even more data coming in. Hundreds of sensors send telemetry back to the garage and to the factory, with entire armies of engineers watching every parameter in real time. All this isn't just about winning races. Formula One is a laboratory, with bleeding-edge tech creeping into road cars. The Mercedes AMG One hypercar, for example, runs a detuned F1 power unit. Energy recovery, electric boost, advanced hybridity, what starts at the track often trickles down to tomorrow's family sedans. 10 years from now, the regular commuter vehicles may be loaded with tech first proven in F1. It's the trickle-down effect of racing's relentless push. But here comes a dose of reality. These power units cost millions. The Mercedes engine program, at its peak, burned through $400 million every year. That's over $1 million a day. Each engine is hand-assembled in rooms cleaner than surgical theaters. Logistics rival those of priceless art. Engines travel in climate-controlled, shock-proof cases with GPS and accelerometers. As for talent, the people behind these monsters are the best on Earth. Multiple PhDs, obsessive attention to detail, and nerves of steel. Every mistake is a disaster waiting to happen, and a blown engine is millions lost in a breath. And as mind-blowing as these machines are, their future is always up for debate. F1 could go even further on electrical power, switch to synthetic fuels, or experiment with hydrogen. But the engineers, they're already cooking up ideas for the next leap. Impossible standards are their bread and butter. Let's zoom out for the big picture. An engine like this shouldn't exist. It's outrageously tiny, takes more punishment in a single race weekend than most commuter cars do in their entire lifetimes, and smashes through the ceiling of what once seemed possible for internal combustion. Yet, here we are. These machines are monuments to human curiosity, defiance, and ambition. Who needs 1,000 horsepower for a commute? No one. But Formula One says yes, and proves that the pursuit of speed, of breaking boundaries, of testing the edge, matters. Every time an engineer says it can't be done, there's someone else willing to work harder, longer, and with more obsession until, suddenly, it can. Here's a thought that stays with you. As engines get better and more efficient, do they lose their soul? In some ways, maybe, but in others, they become even more special. It's not just the numbers, it's the spirit, the beauty of pushing against the impossible, of building for the sake of discovery. This isn't about logic or practicality. It's not about fuel savings or environmental sense. Formula One's power units exist because deep down, humans are driven to push beyond yesterday's achievements. Today, it's 1,000 horsepower from 1.6 liters. Tomorrow, maybe it's 2,000. Maybe one day, engines will sip unicorn tears or become ghosts of silent perfection. But as long as those impossible dreams are out there, someone somewhere will take the challenge. So the next time you hear someone laugh at the idea of 1,000 horsepower from a palm-sized engine, just smile. Somewhere in a lab or garage, teams are bending physics, breaking rules, and aiming for more. Formula One power units are proof that even the hardest limits are just invitations to try harder. In a world obsessed with slow progress, sensible numbers, and compromise, Formula One is that wild flash of brilliance yelling, "Why settle for good enough?" Give brilliant minds infinite budgets and permission to dream. They'll show you just how far human ambition can go. Long may these tiny monsters scream at 15,000 RPM. Because deep down, they're carrying the hopes, audacity, and relentless spirit of everyone who's ever looked at the limits of what's possible and said, I bet we can do better. And in the end, isn't that what it's all about? CTA to end this. If you're fascinated by how modern engineering keeps breaking the rules, don't just watch, join the conversation. Smash that like button, drop your wildest engine predictions in the comments, and hit subscribe for more mind-bending stories from the edge of automotive possibility. Share this video with a fellow gearhead or science fan, and stay tuned, because the next breakthrough is always just a rev away. Experience the thrill, challenge the limits, and never settle for just good enough.